When the camera was invented, it became possible to obtain a photographic record of almost everything of scientific value or human interest through the lens. To most of us, a lens is a thing of glass with mysterious properties that somehow makes it possible for us to record our progress through the years, our weddings and sporting events, and the major and minor incidents of the times in which we live. But in truth, the lens is a thing of beauty, an accessory to the human eye, and the making of lenses is a science out of which has grown the optical industry. To excel is to prosper. In no other industry does this apply more aptly than in the optical industry, where skill in craftsmanship is of the highest importance. All lenses and prisms have one thing in common. They're made of glass. It's the quality of this glass and its chemical composition that are important. Optical instruments are produced from a welter of figures. It often takes as much as a year to complete the data and mathematical calculations necessary for the making and arranging of a set of lenses in an instrument, to give it the required properties necessary to perform its particular job. Mounted in various ways, lenses may help to follow a favorite horse to the winning post, to photograph a pretty girl on the river, to navigate a ship at sea, or serve 100 other uses. The products of this industry are used in war as in peace. Binoculars scan the horizon. The aerial camera reveals secrets that camouflage has endeavored to conceal. And the rangefinder makes marksmanship an exact science. The optometer tests the eyes without fault, doing away with old methods of trial and error. The toolmaker's microscope is just as accurate in finding faults in the manufacture of an aircraft or a family car. As a result of the industry's contribution to the war effort, many technical advances have been made that will be of great value in the future. Optical glass is ground and polished to an incredible accuracy. Here, for example, is a lens surface being tested. Any unevenness of surface is magnified 40,000 times and compared with a finely tooled metal surface at the same magnification. The instrument that is used for the test is itself a product of the optical industry. If any unexpected developments are encountered during research work, every advantage is taken to put them to practical use. Out of this research, for instance, has emerged this thread-cutting machine, used for the mounts of lenses, and a host of other time-saving devices. Before the war, sand used in the optical industry in this country was imported from abroad But today, that essential ingredient is mined from the highlands of Scotland. It is then purified and mixed with the other ingredients according to the formula. Pots made of fire clay that have taken 3 weeks to make are then left to dry for 6 months and preheated in electric furnaces. Then they are hoisted hydraulically into gas furnaces, after which they are filled with the mixture. This is done gradually to ensure even melting, the time factor being of greatest importance. Furnace temperature is taken at regular intervals. The pot is then lowered, much skill being needed to handle the white-hot container filled with molten glass. The temperature of the melt is taken again. Covered with a hood, it will now be allowed to cool gradually. When cold, the pot is broken away, disclosing a mass of solid glass. This, in turn, is broken, shattering naturally along its lines of cleavage. From this mass, pieces are selected for size and perfection. The chosen pieces are subjected to further gradual heating. Then they are finally melted sufficiently to allow for molding into any of the 2,000 or more sizes and shapes now in use in the industry. After the final stage of annealing, the molds enter their process of refinement. With the help of machines designed especially for this work, the pieces are ground and beveled preparatory to smoothing and polishing. This applies particularly to prisms, which because of their shape require special attention. The pieces are then individually set in pitch. Now they are placed on metal laps in such a way that the proper curve is consistently held. Roughing, smoothing and polishing are operations necessary to all forms of optical glass. The pieces are worked to a millionth of an inch, which is the everyday standard of measurement here. The process is carried on amid a symphony of sound and movement and color as the polishers rotate against the surface of the protesting glass. Where lenses are set in pitch, prisms are embedded in plaster of Paris. But beyond this, the process is the same. As the work progresses, more and more attention is paid to cleanliness and accuracy. The lens has been centered, and now it is to be edged. It's hand polished for the last time and then tested. This is done visually at first by the reflection of light waves from two surfaces. In more exacting work, the interferometer is used, giving an accuracy of 1/1,000,000 of an inch. Representing as they do an inaccuracy of 1/50,000th of an inch, the disappearance of these rings indicates a perfect surface. When pronounced satisfactory, the lenses are cemented together to form components for rangefinder, binocular, or whatever it may be. This cementing is done with balsam gum, and much care is taken that no particle of dust should find its way between the component parts. After a period of baking, the components will be mounted, the mounts being the frame on which the glass optics are set at the exact angles and distances from each other that is demanded by the mathematical formula. When mounted, the lens may go either to project films or to make films in various parts of the world. Few people know that most Hollywood productions are photographed through lenses made in Britain. The camera is the mechanism which drives the film intermittently past the lens, the lens mount being set at a precise distance from the film. The amount of light penetrating through a lens is called the F value and is expressed by a number. One of the optical industry's newest developments is the coating of lenses with a special preparation to reduce loss of light by reflection from 10% to less than 1.5%. This serves to increase the F value by that amount. This coating process, which we see in operation here, is used, for example, in making night binoculars for our seamen. During the war, a shortage of binoculars was overcome by the nearest approach to mass production yet applied anywhere in the industry. Prisms and lenses were set in frames by machines erected at short notice. In this way, without losing any of its treasured accuracy, the industry was able to accelerate the production of a much-needed instrument. peacetime, human endeavour turns to things constructive, and the British optical industry reflects in its own fine products the determination to supply none but the best, optical micrometers. Survey and meteorological instruments. Light testing instruments. Microscopes to aid in research. And telescopes to see into worlds unknown to us in the infinity of space.